All right, let's have a go at modeling this rotating mechanical system. uh, this system has two inertias in it, a couple of springs, some frictions. It's driven by a source of angular velocity on the left, and it's loaded by a source of torque on the right. So this is very similar to the one inertia system we looked at yesterday. It's only a little more complex because there are a few more elements we need to deal with. Like usual, we're going to start by working out how many states we need and what we're going to choose as states. Thankfully, the questions told us that we should use energy variables as states, which is often going to be the case for us. We've decided we'd like to do that to find analogues between the different domains. So looking at this system, I've got 2 degrees of freedom present. There are two inertias and they can each rotate about one axis. So there are 2 degrees of freedom, which means I need 4 states. And if I choose energy variables, then I'm looking for generalized momenta and generalized position, which of course in this domain correspond to angular momenta and angular positions. So I'll have L of J1, angular momentum of J1, I'll have L of J2, and I'm also probably going to have a theta 1 and a theta 2, or in this case, because of the unfortunate naming convention used in the question, I'm going to be after theta 2 and theta 3, the thetas that correspond to the J's. So because I like to do my position states first, I'll go theta 2 and theta 3. And they're going to be Z1 through Z4. Alright, after the states, I need to define my inputs. And it's natural for us to want to choose, for example, angular velocities and the torque as the input. Certainly we're going to need the torque as an input. It's going to show up on the free body diagram for J2, so we should choose that one. And much like what we did in class, the source of angular velocity might not find its way into our state space equations. I suspect that's going to be the case. We can always come back and change our inputs if we need to. So for now, I'm going to choose U2 is equal to theta 1, which of course is going to be the integral of that source of angular velocity. Alright, states, inputs. Has the question asked for any outputs? Let's take a look. Driven by a source of angular velocity, loaded by a source of torque. If possible, write state space equation matrix forming construct a block diagram. Right, the question hasn't asked for any outputs. You can of course choose your preferred interesting variable as an output. I'm going to say none applicable, and maybe we can come back and choose some at the end. Next we're going to need CCRs, the relationships, if you like, the miniature models which govern how each of the components in the system work independent or irrespective of how they're connected. So I'm going to need some for the springs that are present, some for the frictions which are present, and some of course for the inertias. So let's be a little bit general. Inertias, springs, and frictions. Remember in this course we're going to use a linear viscous friction model for all the frictions that we see. Of course that doesn't mean that it's correct for every situation you're going to encounter, but certainly it's good enough for what we want to do, which is get the point across of how to model these systems. So wherever I see a friction, I'm going to say that the torque of that friction I is equal to the friction constant of that friction I multiplied by the speed of the shaft to which that friction is connected, omega I. For any springs, I'm going to say that Ts for the spring I is equal to 1 on C, the compliance of that spring I, multiplied by its deformation. And for rotating systems, I like to use capital delta theta to suggest that I'm talking about a change in theta. Finally, for the inertias, wherever I see an inertia, L of Ji is going to be equal to Ji times omega I. So that is the inertia of that mass, of that inertia, multiplied by its angular velocity. And the derivative of that L, the derivative of that angular momentum, is of course going to be the net torque acting on that body. Alright, that's all of my CCRs. I've accounted for the springs, I've accounted for the frictions, I've accounted for the inertias. So I can now start looking at my SSRs. Remember, I like to, and I encourage you to, define all of my deltas and my VRELs so that you know which direction the torque should act when you draw your free body diagrams. You can of course do this the opposite way. You can start by drawing the torques on and try and work out what delta gives rise to that. But particularly in rotating systems, I find that quite tricky. So I'm going to start by choosing my deltas. I'm going to need a delta for spring 2, that's this one here, and I'm going to need a delta for spring 1, which is this one here. Let's start by thinking about spring 2, the one that I've coloured in red. I can choose theta 2 minus theta 3 if I'd like, and remember, if we subscribe to the right hand rule, then theta 2 is going to look like this, and theta 3 is going to look like this. So I could choose theta 2 minus theta 3 as my delta, or I could choose theta 3 minus theta 2. It doesn't much matter, as long as we're consistent between our choice here and what we draw on our free body diagram, we're fine. I think we should choose theta 3 minus theta 2, just based on the way these things are rotating. So I'm going to say that delta theta for spring number 2, C2, is going to be equal to theta 3 minus theta 2. And while we could think about this when we get to the free body diagram, while we're fresh in our head about what we've chosen for delta, I like to also think about what direction the forces are going to act, or the torques are going to act on the inertias that are connected to that spring. So if I've said delta is theta 3 minus theta 2, then in order for that to be a positive quantity, I require theta 3 to be greater than theta 2. And it's in that assumption that theta 3 is greater than theta 2 that we work out which direction the torques are going to act. So you can imagine grabbing J1 and grabbing J2 because they're connected to the two sides of that spring. So you're grabbing J1 and you're grabbing J2, and we're going to twist them both positive with respect to their coordinate system. So in this case, we're going to twist them both downward. And what we want to do is twist J1, the thing which is on the theta 2 side, less than we twist J2, the thing which is on the theta 3 side. So that's the same as saying let's hold J1 stationary and turn J2 positive with respect to its coordinate system. So if you can imagine that you're holding J1 stationary and turning J2 downward, then the torque that acts on J2 is going to want to pull it back up due to that spring. You're twisting it down, it's going to want to pull you back up, which means that on J2 you're going to have a torque which looks like this. And you can imagine that if you were holding J1 stationary and you were twisting J2 downward, the spring is going to want to pull J1 down. In other words, on J1 you're going to have a spring torque that looks like this. Okay, that's one down, one to go. For C1, we can define delta as theta 1 minus theta 2, or we could define delta as theta 2 minus theta 1. Again, I'll draw the arrow on there just so it's clear which way theta 1 is pointing. I guess more for consistency than anything else, I'm going to take theta 2 minus theta 1, the thing on the right minus the thing on the left. But that doesn't mean it's the only way to do it. In fact, I encourage you to do it the other way. But I'm going to say that delta for C1, delta theta for C1 is going to be theta 2 minus theta 1. And again, we can think about which direction that means the torque is going to act on the bodies which are attached to that spring. So if I'm saying it's theta 2 minus theta 1, imagine holding theta 1 stationary and turning theta 2. If you turn theta 2 downward, then the spring is going to want to pull it back upward. So much like what happened with J2, we're going to see this kind of thing happening. Notation, that should have been a 2. We're going to see this kind of thing happening. This guy is going to go like that, TS1. Alright, now that we've defined those, we can think about what the omega i's for the frictions are going to be. This is just like defining our VRELs for dampers. So if you like omega for friction 1, for B1 is going to be omega for B1, we're talking about omega for this friction just here. Well, that's just the omega of the shaft at that point. So if you like, I'll colour in that shaft. It's everything which is on this shaft, which is travelling at omega 2. And if you like omega for B2, by the same kind of thought process, well, the damper for B2 is attached, or the friction for B2 is attached to this shaft, which is travelling at omega 3. Alright, finally we should draw our free body diagrams. So here is inertia J1, here is inertia J2. Which direction's positive for these guys? It is pointing toward the right in both cases. So we can draw that on. And now we can start to draw on the torques. So for J1, which is the friction on the left-hand side, I have spring torques on either side of it, and I have a friction torque which should oppose its motion. So TS1 is going to be this way. TS2 we said was going this way. And because theta points to the right, because the positive direction of motion points to the right, we're going to take the friction torque as pointing to the left. It's TB1, I believe. That's right. And for J2, we have TS2 pointing to the left. And we have T of T on the right-hand side also pointing to the left. TS2, T of T. And we have a friction, which of course should oppose motion. So that one should also be pointing to the left, TB2. If we write out Newton's second law, sum of torques for number 1 is going to be plus TS2 because it's pointing in the same direction as motion, minus TS1 because it's pointing opposite to the direction of motion, minus TB1 because it's pointing opposite to the direction of motion. And on the other side, sum of torques 2 is going to be minus T of T, minus TS2, minus TB2. Alright, we're up to state space equations. So remember, in this section we're looking for the derivative of every state in terms of the states, the inputs and constants. So Z1 dot. Well, my four states were theta 2, theta 3, LJ1 and LJ2. So a Z1 dot is ddt of theta 2, which is omega 2, which, despite the terrible naming convention they've used in the question, omega 2 is the angular velocity of inertia J1. So I should be able to write every angular velocity as a momentum divided by an inertia, much like I can write any linear velocity as a momentum divided by a mass. So that's going to be LJ1 on J1. Which was Z3 on J1. Alright, Z2 dot, that's ddt of what they've called theta 3, which was omega 3, which was LJ2 on J2, which was going to be Z4 on J2. Those were the easy ones. It's time now to do the hard ones. Z3 dot. For Z3 dot, I'm looking for the derivative of LJ1. So I'm looking for LJ1 dot, if you like. And our CCRs tell us that that should be a sum of torques. That's this guy just here. So I'm looking for the sum of torques on inertia number 1. Our SSRs tell us what that sum of torques look like. It's right here. The SSR says that it's TS2 minus TS1 minus TB1. TS2 minus TS1 minus TB1. Well, TS2, according to our CCR, which is up here, TS2 should look like 1 on C2 delta theta 2. 1 on C2 delta theta 2. 1 on C2 delta theta 2. And TS1 should look like 1 on C1 delta theta 1. Finally, the CCR for the friction, according to the friction CCR, which is up here, should be TB1 equals B1 omega 1 minus TB1, which will be B1, and I should be careful. Again, naming conventions have come back to bite us. We'll just quickly check that the friction B1 is actually on the shaft omega 2. So according to what we said here, omega for B1 should be omega 2. Okay, writing these out. 1 on C2 delta theta 2, according to the SSR we defined, was theta 3 minus theta 2. And minus 1 on C1 delta theta 1, which again, according to the SSR we defined, was theta 2 minus theta 1. Minus B1 omega 2. Well, omega 2 we've seen before. It was up here, which was here, which was here. Z3 on J1. So we can just go Z3 on J1, and we can be happy that we've completed that part. A little bit more working to do. We just need to replace these with their state variables. So it's going to be 1 on C2 theta 3 minus theta 2, which is 2 minus Z1 minus 1 on C1, theta 2 minus theta 1, which was going to be Z1 minus... Theta 1 isn't one of our states, but thankfully, I believe we chose that as an input. It was U2. Minus B1 on J1 Z3. Good start. One more to go. Z4 dot is LJ2 dot, which is the sum of torques acting on inertia 2. So now we've got some more torques to write out. If we have a look, we already did this one when we did our free body diagram for that inertia. It's minus T of T minus TS2 minus TB2 minus T of T minus TS2 minus TB2. Well, T of T was also an input. It was U1, so we can replace that one straight away. Minus TS2. Well, TS2 we've seen before, so there's no reason for us to have to rederive it. It was here, which was here, which was here, which was here. So that one is 1 on C2, Z2 minus Z1. Minus TB2. Well, TB2 is going to be B2 times whatever omega is attached to that B2, and according to the SSR, the omega for B2 was omega 3. So it's B2 omega 3, and if we write these out, U1 minus 1 on C2, Z2 minus Z1 minus B2, well, every angular velocity which is on the same shaft as an inertia should be able to be written as the angular momentum of that inertia divided by its inertia. So much like we had before, B1 on J1, in this case we're going to have B2 and it's going to be 1 on J2 Z4. So 1 on the second inertia multiplied by the angular momentum of that inertia, which is Z4 or L2. And that's it. The question also asks you to write your state space equations in matrix form and construct a block diagram. I'll leave that one for you guys to do as homework. Hope this helps.